Okay, yesterday we ended on the properties of logarithms. So let's just try to review this. The first property that we looked at was if you have the log to base a and you're taking the log of the product x into y to base a, this is the same as log to base a of x plus log to base a of y. 2, of course, this is, if you look at the log function, it is only defined for positive real numbers, because if you recall, well, this is what we drew. This is y, this is x. So we said it will pass through 1, 0. So this side, this acts as the vertical asymptote, and the graph goes like that. So the x equal to 0 is actually our vertical asymptote. You can see that the graph will never touch it. And this is exactly y equals log to base a of x. It is assumed that this a is greater than 1. However, when a is between 0 and 1, we expect to have a graph which is going to look like so it will be to come like this, to approach that, but as it passes here, it goes like this. And you can see that this is y equals log to base a of x. This happens when a is between 0 and 1. We have a decreasing function. Okay, and then there we have an increasing function. So this product is assumed to be positive. It's supposed to be positive. It cannot be zero. And then log to base a of x over y. This would be log to base a of x minus log to base a of y. And then the other property we looked at was if you have log to base a of some power, x to the power n, this you can write as n into log to base a of x. Then fourthly, we looked at log to base a of a is always equal to 1. The other things that we'll now look at, how do we change bases? How do we change bases? Of course, before I do that, we have what we call the common logarithm. Common logarithm. On your calculator, it will be written like log of x, just like this. But it should be understood that it is meant the base is 10. Similarly, we have, you can have log to base e of x. On your calculator, you see it as ln x. So it should be understood. And this e, it's a number between 2 and 3. It is actually the limit of some function which I will not, which I will not dwell much on, but it should be known. But how do we change from one base to the other? So if you want to change, say we are in base A, and we want to change to another base, so it should be log to the new base, log to the new base of x over log to the new base. This, you are taking log of the odd base. So this is the formula that we can use. So whatever new base that you are looking at. For instance, if you have log to base a of the number b, it will just be log. We want to change to, say, to some base c, so it will be log to base c of b over log or to base c of the odd base. So it will come out to be like that. Okay. Yeah, so it will be something like this. So okay, we can look at the evaluation of logarithmic expressions. Evaluation of logarithmic expressions. we had indicated that when you have y, also recall that if y is log base a of x, then actually there is equivalence. Then we can write this as the base. It's the power to which the base must be raised to give this number x. So when we have this, we should be able to get to this. This is the base. This is the log. And that's the number. So we can quickly write this. When we are given this, we can write log to base a, okay, of the number x is equal to y. So we can use this. Then the other thing is that I think, if you recall, when you look at the graphs, you see that when you try to draw a horizontal line which cuts, which is actually parallel to the x-axis, this line will cut the graph at exactly one point. So this is a one-to-one function. So if it's a one-to-one function, we expect the following. So since f of x equals log base f of x is 1-to-1, then the following must hold. So we are saying whenever we have x1 equals this, which is in this particular case, it will mean the same thing as log to base a of x1 log to base a of x2. Then, so whenever this happens, then it means the two arguments, this one and that one, must coincide. So we'll use this fact to evaluate logarithmic expressions. Okay, say if you are asked, example would be evaluate the exact value of a log to base 2 of the number 16. So all you have to do is you need to look at say you are simply the log, it is the power to which 2 must be raised to give 16. Say, okay, let y be the required log. Then we expect to have 2y should be 16. And then this can be written as 2 to the power 4. But using the fact that the exponential, because this is an exponential function, the exponential function with a equals 2, we know it is 1-to-1. Therefore, we can deduce that y should be 4. So the answer to this is, therefore, log to base 2 of 16 is actually 4. It is the power to which 2 must be raised to give 16. The next example is log to base 3 of the number 27. So, it's the number to which 3 must be raised to give 27 is 3 itself. So that is the answer. Similarly, if you have log to base 1/27, you can write this as log to base 3 of 27 to the power 1. Using properties of logs, you can write this as log 327, and you know this from here it is 3. So we have this will give us minus 3. So now we can quickly look at logarithmic equations. Look at logarithmic equations. So logarithmic equations. So the first one says solve. Want to solve and check the answer. It's always important. So we have log x plus log x plus 1 is equal to 1. The second is the second one is log of x plus 2 equals log 7 plus log x. We can put c by 3. So log x plus 12 equals, there's minus here, minus log of x is equal to log of x plus 3. So we can try to solve these logarithmic equations because each equation involves logarithmic functions. So solution, your A, you check log x plus 1 equals 1. It should be understood that is the base is 10. The base is 10, but using the properties of logs, the base is 10 in both terms. Therefore, we can combine as log x into x plus 1 equals 1. Then we can also recall that log of 10, log to base 10 of 10 is also 1. Okay? So then we can now use the fact that the log function is 1 to 1. So meaning that whenever we have 2 points in the range that are equal, then when we look at the domain, the point, the point that we are sent to that number should be the same. So in this particular case, what I mean, it means the arguments must be the same. Therefore, I can write this equals 10. It's not necessarily cancelling the log as the name of the function. We are using the property of logs. We know it's a 1-to-1 function. Therefore, we can write like this. Then from here, we have x squared plus x minus 10 equal to 0. I think this we need to change something. I believe there is a problem here. It should be 3, 3, 3. so that we have a 3 here. Otherwise, we are going to face problems trying to factorize this. So when you look at minus 10, you have 5 minus 2. When you multiply these 2, you get minus 10. When you add, you get 3. So I can write this as x squared plus 5x minus 2x minus 10 equals 0. Then I can factorize in pairs. So if I do this, to give me x 5 minus 2x plus 5 equals 0. So this will be x plus 5 into x minus 2 equals 0. But we know the product of two numbers is 0. Then what it means, one of the numbers must be 0. At least one of the numbers must be 0. So this implies that either x plus 5 is the one which is 0, or x minus 2 is the one which is 0, or both would be zeros. We know 0 times 0, it is still 0. So solving them separately, we have either x is that or x equal to 2. But of course, we need to check in the original equation. So you see that when x is equal to minus 5, we are going to have log to base 10 of negative 5. But when we check if you check you cannot take, the x, if you look at the domain for the logarithmic function, I think it is only defined for the positive real numbers. So it cannot be defined for negative or reals. So this one is dropped. I believe if we check when x is 2, the left-hand side of the given equation will be log 2 plus log 2 plus 3 is 5. And if we combine this, we have log, then we have 10. When you multiply 2 times 5, it will give us this. And this is 1 because this is base 10. So this and this is the right-hand side. So the solution set as on one point, which is 2. So that is on that question. The B part, we have log we have x plus 2 here equals log 7 plus log x. Of course, it's a good idea that we combine the sum of two logs is equal to the log of the product of arguments. So I can write this as 7x. Using the fact that log function is 1-to-1, I can legitimately write this as that. So from here, if we try to solve this, it will be 6x is 2, and this will give us x is 1/3. I assume if you try to work out that, you should be able to find the solution. You should be able to check that indeed that is the solution. But see, we have log of x plus 12 minus log x equals log of x plus 9. That's what we are given. So combining, we can write this as x plus 12 over x equals log of x plus 9. Okay, then using the fact that the log function is 1-to-1, I can write this as x plus 12 over x equals x plus 9. You can cross multiply our x squared plus 9x equals x plus 12. So this will be x squared plus 8x minus 12 equals 0. Okay? And this one, I believe we can use the quadratic formula, minus b plus or minus b squared minus 4ac over 2a. So if we plug in there, let's see what we get. We are going to have x equals b is 8, so minus 8 plus or minus 8 squared minus 4, a is 1, and now minus 12. So this is basically that, and then 2, because a is 1, minus 8 plus or minus 64 plus 48 over 2, minus 8 plus or minus, I think this will be 1200 and, okay, that is 112 over 2. I think if we try to work it out, we get minus 4 plus or minus 2 square root of 7. You can check that that is the solution. When you check the only solution, the solution set will only have minus 4 plus 2 square root of 7. Please, you can check the details for this. We now move on to inequalities. Inequalities. So if you have I'll give very important result. It's the theorem. So it says that let A, we have B, X and Y be real numbers. And we allow Q to be a rational number. Then this results in 1. So whenever X is bigger than Y, then we can add the same number to both sides. So what we are saying is that X plus A should be, okay, so whenever this is true, we can always add the same number to both sides. Doesn't matter, it could be a negative number or a positive number. That will not reverse this guy. 2, if you have a number, 2 numbers A and B, and A is greater than B, and you have 2 numbers, X is bigger than Y, so we have this is bigger than that, and X is bigger than D, 4 numbers, then we expect then if this happens, then the following holds. Is also true, meaning I can add A plus X, it will still be bigger than adding B to Y. This is great. So meaning we can add 2 inequalities. When A is greater than 0, and we have X is bigger than Y, then we can multiply this A to both sides, AX greater than AY. This will also be true whenever this is true. So what we are saying here is that when you are given an inequality, you can multiply both sides of that inequality using a positive number without reversing the inequality sign. This also holds when we divide. As long as it's a positive number, you can divide both sides with the same positive number without reversing the inequality sign. However, if a is less than 0 and we have x is bigger than y, then if we intend to multiply both sides of this inequality or dividing both sides by this negative number, we expect ax, we expect to reverse this. If you don't reverse, it will be false. So that one will hold. 5, they have two numbers a and b, but both of them are bounded below by 0, meaning that they are positive numbers. And you have another, we have x, which is bigger than y, both of them bounded above or below by 0, meaning that they are positive numbers. So if you have two inequalities and positive numbers are involved, then you can actually multiply you can multiply these numbers involved, and this will not be affected. You can write like this, and this will still hold. Six. In your notes, it says when x is a positive number, then its reciprocal should also be a positive number. It's trivial, but it is important that we state it. So if you have, both two numbers are positive because they are bounded below by 0, or these two numbers, which are negative because they are less than 0, both of them, then please, if this happens, if this is true, then when you take the reciprocal, this should be reversed like this. The reciprocal should be reversed like that. 8. Point number 8, if q is not 0 and you have a positive number, so if you have a positive number and you have a rational number which is not 0, you can raise this number to that power, and the power will still be greater than 0. We don't expect when you raise this positive number to either negative rational number or positive rational number to change the sense. It should still remain positive. That is important. 9. If you have q which is positive and two positive numbers are involved and they're related like this, so if you have two positive numbers, you can actually raise both sides of this inequality using this without tampering with the inequality symbol. So y to the, it should remain the same. It should remain the same. It should remain the same. However, if your q is less than 0 and the two positive numbers are involved, 10, so we are saying Q is less than 0, and we have an inequality involving two positive numbers, then if we raise this to a negative rational number, this must change the sense. I think this is, we can check just to illustrate what is happening here. Say you have two, an example to this last one is, if you have 2 is less than 4, this is the known fact. So choose your Q to be minus 2. So if you choose your 2 to be minus 2 and you raise each one 2 to the power minus 2, this we don't know whether it's a 4 to the power minus 2. You see that this number is the same as 1 over 4. This is the same as 1 over 16. It's saying 1 over 4 is less than 1 over 16, which is wrong. It's definitely, this is not true. Okay, it's because we have disobeyed what this is saying. So saying when it is raising both sides to a negative power, this inequality symbol must be reversed too. So that is very, very important. It must be reversed. So if the other, maybe just to talk about 9, an example on where we said Q positive and X greater than 1. This, we are saying it implies X to the power Q should be bigger than Y to the power Q. You can look at an example which we know about it. This is 39. Hello. Oh, okay. An example that you know very well could be if you have say absolute value of this, say you have absolute value of this, look at this. So according to this result, because we know these are non-negative reals involved, then I can happily do whatever I want. I can raise both sides using Q2. I can write like this without problems. But I know that we know absolute value of X is the same as, okay, if you have a 2 here, you can also write like this. It is coming from the fact that absolute value of a number is always equal to, so if you square both sides, you will get this. So instead of having this, I can therefore write this as x to the power 2 is greater than 1 to the power 2. And this is quite important when you are dealing with inequalities which involve absolute values. So this will be quite useful result. We are able to do that because of this result. So quite important. So we can now look at some examples. An example on linear inequalities, we have linear inequalities. An example that we could look at is, we can look at simplifying the following inequality. We are given 6x minus 3, and as 3 is less or equal to 21 minus 2x. So if you look at this, we have to apply those 10 properties. We need the terms with x to be on one side and those without to be on the other side. So what I can do is I can add both sides by 2x, because I know x is a number, double that number is still a number. So I can add that number to both sides without tampering with this. So if I do that, I'll have this is less, okay, minus 3 is less 21. Then I can add 3 on both sides. I'll have 8x is less or equal to 24. Then I can either multiply by 1 over 8, which is equivalent to dividing by 8, because 8 is a positive number, I will not change the sense, so it will just be 3. So the solution set, it is the set of all real numbers such that this number is 3 or less than 3. So we can now look at absolute values involving inequalities involving absolute values. So let's look at absolute value inequalities. Absolute value inequalities. Absolute value inequalities. This I'll state in form of a theorem. So let A be a positive number. Then the following holds. So the following is true. 1, if I'm looking at the absolute value of a number, I say I can either have less than or equal to, it doesn't matter. When you have this, whenever this is true, then it means this x is between, this x is greater than or equal to minus a, or it is less or equal to a. So it means this x is between minus a and a, as long as this is a positive number. 2, absolute value of x is less or equal to, is greater or equal to a. What it simply means is, this is true. This equivalent statement not involving absolute values would be either x is less or equal to minus a, or x is to the right, or it is at a. 3, I need to put an equation like this. So whenever we say the absolute value of a number is equal to a, where a is positive, we can get an equivalent statement not involving absolute values. So this would mean that the x is actually minus a. We know my absolute value of minus a, because we have minus a, I can write like this. into A. So, but absolute value of that it is 1, so it will be like this. So in either x is minus A or x is A itself. So that you have, so it means it is, so these are the two possibilities. Remember, A is positive, so it's positive, so this is a negative number, minus A is negative because A is known to be positive. So either x is minus A or x is A. So these are quite important. It's an equation, it's not an inequality. This is an equation involving absolute value. These are inequalities, okay? These are inequalities because of the less than, greater than. Okay? So either we can have less than here, or we can even have here less than, and here we can have greater than. Doesn't matter. The rule still just needs to change here, where here it will now be less than, there less than. In case we have this, then here it will be greater than. Okay, it will be strictly less than, and here it will be strictly greater than. Okay, so we have to remember that. Very, very crucial, very, very important. So we can look at examples. Example. A, we have the absolute value in your notes of absolute value 2x minus 3 is less or equal. We need to solve this. Solve this is less equal to 7. And B, we have the absolute value of 3x plus 1. It is greater than 8. So, we'll start with A. So your A here is 7. You have 7 there. So you can write it like that. So this 2x minus 3 is less or equal to 7 is equivalent to the statement minus 7 is less or equal to 2x minus 3 less or equal to 7. And then this is a double inequality. It's a double inequality. What it means is this is a double inequality. Double inequality. So if you want, you can solve it. It means minus 7 is less than this, and 2x minus 3 is less or equal to 7. So if you solve this using the way we had done it before, you will see that this will be minus 4 is less or equal to x, and 2x is less or equal to 10. Solving this by dividing by 2, so we are going to have minus 2 is less x, and this one x is less or equal to 5. But and is associated with the intersection, right? So we are having, we end up having so the solution set for this, we are saying it is the set of all x such that minus 2 is less or equal to x. So we have to take the intersection, this side, all x less or equal to 5. If you want, you can even write these sets as intervals, where you are saying minus 2 is less than or equal to x. Or you are saying x, which is the same as x is greater than or equal to or minus 2. So x is to the right? So you have minus 2 as the then comma, it's going to infinity, right? Okay, intersection. Here in interval notation, the maximum is 5. So you have minus infinity and 5. You have this. Please here change to that because the endpoint is included. So if you use the number which we exhaustively looked at, you have minus 2 here and you have 5 here. Okay, so this one is like you have 2 going to positive. It's this one. And then for this one, it's including the endpoint and we're going to the left. So the intersection is this part. So it will give you the interval minus 2 to 5. So this is your solution set to this problem. So the solution set is actually the set of all x such that minus 2 is x less or equal to 5. Or in interval notation, you can write this as minus 2 to 5. Okay? So that is how you solve this one. Solution to part B. Solution to part B. We have 3x plus 1 plus 1, we are saying is greater than 8. So we have to write this in the form which is equivalent to this, but not involving absolute values. But this is equivalent to saying 3x plus 1 is less than minus 8, or 3x plus 1 is greater than 8. So we can solve this. Remember, I'm saying or here, so we have 3x is less than minus 9. You can, x is minus 3, or you try to solve this, 3x is greater than 7. So you have something like this. We are using or. Or it means you are going to take the union of the associated sets. The union of the associated sets. So we are saying solution set is a set of all x such that x is this, or x is greater than 7 over 3. If you want, you can even separate them. Union, the set of all x such that. So that's what you have. But if you take the union, you have minus 3 and you have 7 over 3 here. This one is coming this side. This one is going that side. So there's no way you can simplify it. So this is the correct solution set. Now we can move on to look at quadratic inequalities. Quadratic inequalities. So we look at quadratic inequalities. Okay, so we have, instead of quadratic equation, now the equal sign can either be replaced by greater or equal to, or less than or equal to, or strictly greater than, or the quadratic equation, they can involve quadratic function where you involve something like less than. So just when you have only this, you call it quadratic equations. Ax squared plus bx plus c is equal to 0, right? So when this is replaced by either of these, it is called quadratic inequality. So how do we handle such problems? So we explain what is done using an example. So examples will make it clear. So example, solve the first A says x squared plus 8x or plus 3x, please, 3x minus 18 is greater or equal to 0. B, we have x squared minus x minus 8 is less than or equal to 4. And C, we have x squared plus 2x plus 3 is greater or equal to 0. D, we have x squared minus 3x minus 5 is greater or equal to 0. So they have the same form. So I'll provide a solution to A and I'll leave B, C, and D as exercises. So, but that's the way it is supposed to be done, is that step 1, consider the associated equation. Whether here it was strictly greater than or strictly less than, we have to consider an associated equation. So associated equation is x squared plus 3x minus 18 is equal to 0. So we try to solve this. When we look at factors of minus 18, which will give us the sum, so it is 3 and minus 3. So I have x squared plus 6x minus 3x minus 18 equals 0. So here we'll have x plus 6, okay, minus 3, then x plus 6. So this will be x plus 6 into x minus 3 equals 0, right? And this, when you solve, it will give you this, or x is 3. Step 2, use the solutions in step 1 to divide up the real number. So you have got, this is your number line. You are going to use minus 6, then you have 3. So this is partitioned into 3 segments. So you can pick, so in each interval, you can pick what we call a test value. So pick any real number, test value, any number which is to the left of minus 6. You can pick, say, x here, we'll pick minus 7. The test value here, I'm going to pick any number between minus 6 and 3. I conveniently pick 0. I could have picked 1 or so. Then the test value, 3 going to the right, I can pick my test value to maybe I can pick 4. I don't want to pick big numbers. Now, when you look at this, it's saying less, greater than, or equal to. Where it is equal to, it is equal to when x is this, or minus 6, or when x is exactly 3. That's where equality is. If it was just greater than, I was going to exclude these points, but using them just to subdivide the number line. Okay? Then, I'm interested in where it is greater than. So normally, it's advisable to use remember we are saying after factorizing, this is what we are having. So it's like x squared plus 3x minus 18 is actually equivalent to this plus 6 over, x minus 3. So it's in factored form. This is what we are given here. So after factorizing, we are having this part. So these are equivalent statements. So I want to see what happens to this quantity when I'm in each interval. So when I'm in the interval negative infinity up to minus 6, let's see what happens. It's going to be, I've picked minus 7, so I'll use the factored form. The first brackets, minus 7 plus 6, it's a negative number, then times. Minus 7 and minus 3 to be a negative number. Meaning the product here is positive. What it means this is positive or it's greater than 0 here in this region. So it's greater than 0 there. Then I come to the interval between minus 6 and 3. I'm using the test value 0. So the first bracket, it is positive. The second bracket, 0 minus 3 to be a negative number. So positive and negative, it means it's negative or less than 0. A negative number, we say it's less than 0. Okay? And then when we are to the right of 3, we have picked the test value 4. We are only interested in the sign. So the first bracket will be a positive number times 4 minus 3 is still a positive number. Positive, so it means it's greater than 0 here. So where this is greater than 0, it's here and there. Therefore, your solution step 3, you can state your solution set. Solution set S. It is simply the set of all x such that this x is less than or equal to minus 6, or this x is greater or equal to 3. Remember the endpoints are included because that's where equality is. So that's the answer. So we move on to what we call rational inequalities. Rational inequalities. Rational inequalities. So inequalities involving one or more rational expressions are rational inequalities. So you can have a rational inequality is the one which will take the form. We can have numerator and denominator, where these are polynomials. They are polynomials, right? And we can also have something like greater than or equal to 0 here. So this is a rational inequality. Or strictly, let's look at an example. An example is, this could be anything. Maybe we could put A here, where A is a real number, something like this. So an example is, look at 2 examples. We solve A, we are given 5 over x plus 4. It should be greater than or equal to 1. B, we have 2x linear term, and we have 3x plus 4 as our denominator. This is less than 5. In the notes, I've outlined the steps that should be followed. So step 1, rewrite the inequality if necessary so that 0 is on one side and there is a simple fraction on the other side. Step 2, determine the values that will cause either the numerator or denominator of a rational expression to equal 0. These values determine the intervals on the number line to consider. So step 3, then we can use those values as we can use them as to divide up the number line. So let's quickly see what we are talking about here. Okay, solution to part A. As advised, you have 5 over x plus 4 is greater or equal to 1. So, but I can subtract 1 from both sides. So our 5x plus 4 minus 1 is greater or equal to 0. So that our one side is equal to 0. So if I do this, then I can put this under the same, I can write this as under the same denominator, x plus 4, 5 minus x minus 4 is greater or equal to 0. But simplifying this, I think we have minus x plus 1 over x plus 4 equal greater than or equal to 0. So we need to determine what we call critical values. So the critical values are points where the numerator is equal to 0, points where the denominator is equal to 0. So these will be x is 1 or x is minus 4. So this will be 0 if you choose your x to be 1, and the denominator will be 0 if you choose your x to be minus 4. Then I'll draw the number. I have minus 4, then I have 1. So I'll test the value here. I can pick minus 5. Test the value here, I can pick 0. Test the value there, I can pick 2. Okay? Do we need, because it also says equal to, if a rational expression is equal to 0 if and only if the numerator is equal to 0. So the only point for equality is when x is 1. So I will include 1. This for x equal to minus 4, it's undefined, so I will not include that point. So let me check. When I take minus 5, this is negative to be positive. So the numerator will be a positive number over minus 5 plus 4, it will be a negative number. So the quotient to be less than 0. So this is less than. If you pick 0 here, this will be positive, 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 positive. So it is greater than 0. If you pick 2 here, you have negative numerator, you have positive. So the quotient, it will be less than 0. So we are interested in where we have greater than. So greater than is just the point there. So your solution set, it is the set of all x such that minus 4, this x cannot be equal to. So I will simply write should be greater than, still greater than 4, but should be less or equal to 1. So this is the answer. Or in interval notation, you can also write this as minus 4 to 1, like this. So let's see how you handle such a problem. So we can solve, let's solve B just in the similar way. So 2x minus 1 over 3x plus 4 is less than 5. But in this, we can subtract 5 from both sides. So 3x plus 4 minus 5 is less than 0, right? I can write this as 3x plus 4 minus, I can put 5 here. Okay. Why not 3x plus 4 over the same thing? I've not changed anything there. It's less than 0. But if I do this, to allow me to write this nicely as 2x minus 1 minus 15x minus 20 over 3x plus 4 is less than 0. Simplifying this, it will be minus 13x minus 21 over 3x plus 4 is less than 0. Remember here now it's still less than 0. So, okay. Okay, so as before, we now get the critical values. The critical values here, when is the numerator equal to 0, it's when x is 21 over minus 21 over 13, okay, or when x is minus 4 over 3. So we have got these two numbers which will help us to divide up the interval. Okay, so let's see how these numbers are related, because we have to divide in a number line. Okay, we need to know they are related, which one is to the right of the other. So this is roughly approximate 1 minus 1.62, and this is roughly negative 1.3, something like that. Okay, so if you compare these numbers, we expect, okay, this is like that. So this is far away from 0 and they are negatives. So it's like we have minus 4 over 3 here, and this minus 21 over 13 should be here. Okay, it should be, this is closer to 0 than this one. So this is how they are related. This is how they are related. So here there is no equality, so we'll not include any of them. And after doing this, at least it's giving us the, this is approximate negative 1.62, this is approximate negative 1.33. Okay, so Which test value can you pick here? You can pick negative 1.7 if you want, or if you really want some number, maybe negative 2, maybe negative 2 can work. Here we can pick which number, 33, and we can pick minus 1.3. Yes. On this side, the test value, we can pick something like negative 1.4. Negative 1.4. It has to be, I think there's a problem here. That's not how they. This we can pick negative 1.3, or let's put 4 here. Okay. Yeah. Then here we can pick 30. Yes, that is much better. Yeah, minus this, then this, then this. I think we are fine. We are only interested in seeing the sign for this. So let's quickly work it out. When we pick minus number minus 2, this will be 26. 26 minus to be a positive number. When I pick minus 6 here, plus 4, so it will be positive, negative. So the quotient, it is less than 0. If we pick minus 1.4, we pick minus 1.4, we end up having negative 13 times negative 1.4, okay, then minus 21. So it will be a negative number on top over 3 times negative 1.4 negative, then we add 4 to still be negative. So the quotient, it will be greater than a positive. And assume when you work out this, if you pick that number, negative 13 times negative 1.3, then you subtract 21, still a negative number. When you are in the last interval, then the other one will be actually to be negative 3.9 plus 4. It's a positive number. So meaning that the quotient will be negative. So, and we want where we have this. We have this here or there. Therefore, the solution set, the set of all x such that x is less than minus 21 over 13, or x is bigger than minus 4 over 3. So this is your, for interval notation, you can put this minus 21 over 13 union minus 4 over 3 going to positive infinity. So this is also allowed. So we can write in either form. So we now move on to what we call polynomial functions. Polynomial functions. polynomial functions. Polynomial functions. So a polynomial definition, a polynomial in one variable, say x, is a function P defined by P of x to be a n x to the power n plus a n minus 1 x n minus 1 plus so on a1 x plus a 0. So we can say where ai's I running from 0 to n are constants, or just say are real numbers, and the coefficient, the leading coefficient an is not 0. Is not 0. And this is said to be the nth degree polynomials. This is the nth degree polynomial. So we are going to look at, polynomials. When you are given polynomials, you can add them, you can subtract them, you can multiply them. Expansion in your high school, where you are at 3x plus 4, is a polynomial. You are multiplying it with another one, like if you are adding, say, x minus 1, these are two polynomials. You said you looked for like terms. So you say 4x plus 3. You can also multiply these two polynomials. Okay, or subtract. First, we start with subtracting, where you say this and that, it will be 2x. 4 minus 1 is plus 5. You can also multiply them to allowed, where you say this times that, 3x squared, this time minus 3x plus 4x minus 4, and then you have this, like terms plus x minus 4. Okay? So, but in this lecture, our interest will be on the dividing polynomials. When you are given two polynomials, how do you divide them? That's the one thing I'll focus on. So I will explain the method using, an example that, okay, let's look at an example. So we are asked to divide 3x to the power 3 minus 5x squared. Then we have plus 10x plus 1. And this we need to divide it by 3x plus 1. Okay? So this is a polynomial. The ai's are 5 minus 5, 10. and the constant A0 is, okay? Okay, so you are dividing this by that. This is called the dividend. Dividend. And this is called the divisor. Okay? So when you are dividing, you can arrange the terms in the divisor in the descending powers of x. So since it's a linear, it's a polynomial degree 1, the divisor. So we start with 3x plus 1. Then we come to the dividend. We are going to arrange the terms in descending. Say third degree polynomial. So I'll start with 3x to the power 3 minus this plus 10x. If this was missing, I was going to insert 0x. Plus it is now 10x. That's fine. Then plus 1, the constant term. Then how you carry out the long division? You take this term, you divide it into that. So 3x into 3x to the power 3, the 1x will cancel, the 3's will cancel, you have x to the power 2. You write your x to the power 2 here, below this term with minus 5x squared. Then you take this, you multiply by this, you have 3x to the power 3, this and this, it will give us x to the power 2. X to the power 2, we write it under here, plus x to the power 2. Then you put in brackets before subtracting. So if you subtract, you have 6x to the power 2, you bring down plus 10x. Then you take this, you divide in 2 there. I can see that I will have minus 2x. So I write here minus 2x, where is x? This time that to minus 6x squared minus 2x. You put in brackets before subtracting so that you don't mess up. So I have 12x because minus and minus to be plus. Then bring down the constant term plus 1. Then you have to continue as long as the power here is the same, the power here is the power here, as long as the power here is equal to the power there, or the power here is bigger than the power that is appearing there, you have to continue. So when you divide this time, this into that, we are going to have 4. So plus 4. So we have 3x or 12x, and then we have plus 4. So we put in brackets before subtracting. This will give us minus 3. So minus 3 is called the remainder. Minus 3. So this last one is called the remainder. The remainder. And they are related in the following way. So what we are doing is you have 3x to the power 5x squared plus 10x plus 1, which is the dividend. It is equal to, can you recover it by getting the divisor? You multiply by this, is called the quotient. Quotient. This is the divisor. And this is the dividend. Okay? So you can recover this by saying the quotient 2x plus 4, then you add the remainder, in this case it's minus 3. When you expand there and do that, you should be able to get this. Alternatively, if you divide throughout by the divisor, you end up having 5x squared plus 10x plus 1. If you divide by the divisor, it's going to give you the quotient then plus the remainder over the divisor. This is another presentation. So either you have this one or this one. Okay? So very, very crucial. In the notes, I've given so many questions. on how you can implement the long division. Maybe we can look at another where the one term in the dividend is missing. How we can handle that one. Okay, there we have this one. Another example. It says you have x to the power 5 minus 1, you divide by x plus 1. This is the 5th degree polynomial. How do we handle such a problem? So what you do, x to the power 5 minus, the same as x to the power 5. The term with x to the power 4 is missing, so I will set a 0 as the coefficient. The power 3 is also missing. I do the same. To the power 2 is also missing. To the power 1 is also missing. And then I must have the constant term which is given. In the divisor, that's fine. So when you are dividing, you're going to have x plus 1. So you write this now. 0x to the power 3 plus 0x squared plus 0x minus 1. So as before, you can see we write in descending powers of x. Similarly, so this into the leading term, so it is x to the power 4, you write here, you multiply x to the power 5 plus x to the power 4, you do this, then subtract. You have minus x to the power 4, bring down this, plus 0x to the power 3. It's important to do that. This into that, it will be minus x to the power 3. You multiply minus x to the power 4, minus x to the power 3. You put in brackets before subtracting. So this will be this plus, so it will be x to the power 3. Bring down this plus 0x to the power 2. This into that, it will be plus x squared. So x to the power 3 plus x squared, you are subtracting. So this will be minus x squared. Bring down this plus 0x. This into that, that is minus x. So minus x squared minus x. You put in brackets before subtracting. So that your x, you bring down minus 1. There it will be plus 1. Then it will be x plus 1. Put in brackets before subtracting. And that will give you what? Minus 2. So the remainder is minus 2 and the process ceases. Okay. So what we are saying here is that, and you can verify that if you multiply this times that, let's check this times the quotient, x4 minus this plus x squared minus x plus 1. If we add our remainder minus 2, let's see if it will give us this x to the power 5 minus 1. Let's see. So this one, it means each term here should be multiplied by x. So x to the power 5, x to the power 4 plus x to the power 3 minus x squared plus x. Then this one multiplying everything, x to the power 4, x to the power 3, x to the power 2 minus x plus 1, right? Then we have minus 2. So here I think some things will cancel, this will cancel this, this will cancel this, and this will cancel this, this will cancel this. We are left with x to the power 5, and 1 minus that is minus 1, which is actually the dividend. So let's see, so our result is correct. We can also use what we call synthetic division for a divisor of the form x minus a, we can use the synthetic division. So that will be explained now. So we could use the synthetic division to get the same answer. We said, okay, example, x to the power 5 minus 1 divided by this. Let's use the synthetic division. So what you do is, you ask yourself, what is the divisor? What value of x will make the divisor equal to 0? It's or you can equate this divisor, this x plus 1 equal to 0, and then solve for that. So it is when x is minus 1. So that minus 1, you put it here. Then we just pick the coefficients for this. Remember, the coefficient of x to the power 5, it's 1. The coefficient of x to the power 4, which is missing, I will set as 0. The coefficient of x to the power 4 is 0. X to the power 3 is 0. To the power 2 is 0. To the power 1, it is 0. Then the constant is this one. X to the power 5, 4. X to the power 4, x to the power 3, x to the power 2, x to the power 1, then the constant. This is fine. Then you draw a line here. You bring down the first coefficient, then you say minus 1 times this, it gives you negative 1. You write negative 1 under this coefficient. Then you add 0 plus minus 1, still minus 1. Then you continue, this time is that it is minus 1. You add 0 plus minus 1, still minus 1. You continue, this time is that to give you 1. Write your 1 here, you add, it's 1. Minus 1 here now, adding, minus 1. Then continue, that will be 1. Okay. Just a moment. Minus, there's a mistake here. Because we said bring down this time this minus 1, we write it here. Then when you add this minus 1, then minus 1 times negative 1 is supposed to be 1. So when you add it to be 1 here, then here it should have been minus, adding minus, then here it is going to be plus. This time that it is plus 1, adding to be 1 like this. Then minus 1 times 1 is negative 1. So that when you add here, you have minus 2. So the last number is always the remainder. Then this is constant. This is the coefficient of x, the coefficient of x to the power 2, the coefficient of x to the power 3, the coefficient of x to the power 4. So this gives you quotient. You can read out your quotient. It is now going to be x to the power 4 minus x to the power 3 plus x squared minus x, then plus 1. I think that's what we got as our quotient, which is this one here. Okay, and our remainder is minus 2. So you can only use it when you have it is of this form, the divisor. So I've given some more examples in the notes. Just refer to them. And I've given so many exercises for practicing. So now we I now move on to look at the remainder theorem. Okay, so we look at the remainder theorem. So when a polynomial which in this case I'll call it P of x, is divided by x minus a, the remainder is the constant P of a. That's how we can get the remainder. And it's not difficult to see this, so we can provide a proof. So when P of x is divided by x minus a, let the quotient be q of x, and the remainder Rx, some function Rx. Then we know they are related like this. P of x is going to be the divisor times the quotient, then plus the remainder Rx. This is what we know. Okay? So we want to find out what the Rx will be. So now you can plug in. So putting x equal to a in the equation, let's see what we get. If we do that, we end up P of a, where there is x at a, we end up having a minus a, q at a plus r at a. And this is the remainder, right? So let's see, you see this part, it is 0 because of this, therefore the remainder will actually be P of a. I think that's what is claimed here. So the remainder, which is actually a constant, it's a constant. So let's look at examples. Example. Find the remainder when x to the power 3 minus 3x plus 4 is divided by x plus 3. You could use the long division, the synthetic division to get the remainder, but it's time wasting. It's time wasting. So using the remainder theorem, we can quickly deduce the remainder. So, but let's see, say some by long division, you can say x plus 3 then x to the power 3, there is no x to the power 2, so I insert a 0. Then I have 3x plus constant. So if I do this, it will be x to the power 2, x to the power 3, plus 3x squared. You put in brackets before subtracting. So minus 3x squared, bring down this term. You continue minus 3x. That is minus 3x squared minus 9x. Put in brackets before subtracting. So that will give you 6x. Bring down this plus 4. That will be plus 6. And that is 6x plus 18. Put in brackets before subtracting. We have minus 14 as the remainder. This is the remainder, right? But by remainder theorem, it is simply saying remainder must be P evaluated at x equals, in this case, we are dividing by x plus 3, so the remainder should know x, so you can write this as minus 3. So the remainder theorem is saying you can find the remainder by plugging in the dividend where there's x put minus 3. That's what it is saying. And if we do that, let's see. So your P of x, so we say let your P of x is what is given, x to the power 3 minus 3x plus 4. So your remainder, according to the remainder theorem, is supposed to be P evaluated at minus 3 because you have x plus 3. So you have to evaluate, you have to use the point which makes this equal to 0. So it's minus 3. That's the one that you are supposed to use here. So minus 3 to the power 3 minus 3 minus 3 plus 4. So you have minus 27 plus 9 plus 4. And this, I can see this is 13 minus 27, we have 13. That gives us minus 14. Okay, which is the same. So this is wasting time. This takes longer than this. So the remainder theorem is important. It's a very important result that we can invoke each time we are faced with this problem. Another example. Example says when the polynomial P of x equals x to the power 3 minus 3x squared plus ax plus b is divided by x minus 1, we are told the remainder is negative 4. However, when P of x, the same polynomial, is divided by x minus 2, the remainder is still the same, is also minus 4. So now let's find the remainder when this polynomial P of x is divided by x minus 3. So this is what we are faced with. Okay, solution, we just need to go through this nicely. You know, by remainder theorem, if P of x is divided by x minus 1, the remainder is equal to P evaluated at 1. But P evaluated at 1 will come there to a 1 to the power 3 minus 3, 1 squared plus A1 plus B. This should be the remainder, but it involves B. What we are given when the remainder is minus 4. So this is an equation. Let's see. We have 1 minus 3 plus A plus B equals minus 4. Therefore, A plus B should be, this is minus 2, minus 2 equal to, so this you can call this 1. It's an equation, okay? We have A plus B. So then we are told that when the same polynomial is divided by x minus 2, it gives the same remainder minus 4. But using the remainder theorem, you know it's going to be P at 2. According to them, it gave them minus 4. But what is this? It will be 2 to the power 3, 2 squared, plus A2 plus B equals minus 4. So we have 8, this is 4 minus 12 plus 2A plus B equals minus 4. Therefore, 2A plus B is minus 4. This minus 4, when we cross it, we have minus plus 4. And this is equal to 0. Call this equation 2. So solve 1 and 2 simultaneously. So if you do that, you have we have A plus B is minus 2, and we have 2A plus B is 0. I think this is your 2, this is 1. But from 2, you see that B is minus 2A. So put this value in 1. Where there is B, put that. We have A. Where there is B is now minus 2, A is minus 2. This is minus A is equal to minus 2, which gives us our A is 2. Since B is equal to minus 2A, therefore your B is minus 2, which is minus 4. So these are the values that A is 2. Yes, A is 2 and your B is minus 4. So we can, therefore, the P of the polynomial in question is x to the power 3 minus 3x squared plus our A is 2, so I have 2x, and my B is now minus 4. This is the polynomial, right? So we are asked to find the remainder when this polynomial is divided by x minus 3. Okay? So when P of x is divided by x minus 3, by remainder theorem, remainder is going to be P at 3, evaluated at 3, and this will be 3 to the power 3 minus 3, 3 squared plus 2, 3 minus 4, which is 27 minus 9, this is 27 plus 6 minus 4, so that will be 2. So the remainder should be 2. So the remainder is 2. So we move further. We now look at the remainder theorem. Remainder theorem. The extended form. Remainder theorem, the extended form. So when a polynomial p of x is divided by ax minus b, the remainder is supposed to be p evaluated at the value of x, which makes this 0, the divisor 0, and that's b over a. So we can use the similar argument as before as a proof. So example, find the remainder when x to the power 3 minus 3x plus 4 is divided by 2x plus 3. So yeah, some students waste time to use other methods at their disposal, like the long division. Just to see, how much time we could waste, I can use the long division, assuming that I was not aware about this extended form. I could use the long division. And if you use the long division, you would get, let's see what we would get. This, so x to the power 3 plus 0x squared minus 3x plus 4. That's what I would get. Then this into that, okay, 2x divided by this number, you have x to the power 3 divided by 2x. So this will cancel, we have a 2 there, so it will give you half x squared. Then when you multiply out, it will be x to the power 3, then plus 3 over 2x squared, right? Then subtracting 3 over 2x squared, you are dividing, you are saying minus 3, or you have to bring down this guy here, minus 3x. Okay. What are these? Yes. Okay, so you are dividing, you are saying this divided by 2x, but this is minus 3 2x squared times, it's over 1 over 2x, right? So this will cancel, and then I'm having minus 3 over 4x. You put this minus 3 over 4x here. So this times that, okay, we'll get what? Minus 3 over 4x into 2x. So 1 there, 2 here, but it will give you minus 3 over 2x squared, right? And this one, we are supposed to multiply by 3, so it will be minus 9 over 4x, right? Then subtracting. So that will go, this will be 9 over 4 minus 3, that's 4, 9, 12, that's minus 3 over 4, minus 3 over 4x, bring down plus 4 here. So again, we are dividing, we are saying minus 3 over 4x divided by 2x over 1. So it will be minus 3x over 4 into 1 over 2x. So this will cancel with that and we have minus 3 over 8. Okay, so when this gets there, it will give us minus 3 over 8. So we continue multiplying. It will be 2x times this term. It will give us minus 3 over 4x. Minus 3 over 4x. Then when multiplied by 3, it will be minus 9 over 8. So if you subtract this, it will give you 4 plus 9 over 8. So that's 8, 32 plus 9, which is 41 over 8. So our remainder is 41 over 8. Okay? So it would, that's what we would get. So if we didn't know, we would get that's what we would get, right? After wasting time. But if we use by remainder theorem, it's simply but by remainder theorem, remainder, which we denote by R from now on, is supposed to be the polynomial given evaluated at the value of x, which makes the divisor 0, which will be at minus 3 over 2. So just evaluate the given polynomial dividend using this value minus 3. So that's what it is saying. So but your P of x is x to the power 3 minus 3x plus 4. So therefore your P at minus 3 over 2 to be minus 3 over 2 to the power 3 minus 3 over 2 then plus 4. So this will be minus 27 over remember minus 3 to the power 3, 2 to the power 3, 8, plus 9 over 2 plus 4 over 1, 8. So that's minus 27 plus, that is 4, 36 plus 32. So you have 68 minus 27. This is 1. This is 4. This gives us 41 over 8, which is the same. Okay, so using the remainder theorem, you save time. Okay, as you have observed here. Using the extended form of the remainder theorem. So exercises so please, you have to try the following. 1, find the quotient and the remainder when x to the power 2 minus 5x plus 2 is divided by x minus 3. B, 6x squared minus x minus 2 is divided by 3x plus 1. 2, find the quotient and the remainder when the first first polynomial is divided by the second, in the following cases. So m x to the power 3 plus 2x squared minus 3x plus 1 when divided by this. B 2x to the power 3 plus 4x minus 5 when divided by this. C x to the power 3 minus 3x squared plus 5x minus 4 when divided by this. D 5x to the power 3 minus 3x plus 7 2x to the power 3 minus x squared minus 3x minus 7 2x plus 1. F 6x to the power 3 plus 17x squared minus 17x plus 5. When you divide it by that, 3, find the quotient and the remainder. When A x to the power 4 minus 2x to the power 3 minus 7x squared plus 7x plus 5 is divided by x squared plus 2x minus 1. B x to the power 4 minus x to the power 3 plus 7x plus 2 is divided by x squared plus x minus 1. C 2x to the power 4 minus 4x to the power 3 plus 3x squared plus 6x plus 5 is divided by x to the power 3 plus x squared plus 1. D 6x to the power 4 plus x to the power 3 plus 13x plus 10 is divided by 2x squared minus x plus 4. So more problems will be added. You'll see many problems in the lecture notes to be distributed soon. When the 2x to the power 3 minus x squared plus ax plus b is divided by x minus 2, the remainder is 25. When divided by x plus 1, the remainder is -5. Find the values of A and B. We now move on to the factor theorem. which is also a very useful result. Very useful result. It's called the factor theorem. Factor theorem. A polynomial Q of x as a factor x minus a if and only if. So to say a polynomial as a factor x minus 1 minus a is equivalent to saying the polynomial evaluated at the point which makes the divisor, which makes this factor 0, is actually equal to 0. It's like this is, this like so the statement a polynomial as a factor, this factor is equivalent to saying the remainder when that polynomial is divided by this is actually 0. Very, very useful result. I don't want to, I will not prove it. I'll leave out the proof. Let's see how we use it. Example. Find the factors of x to the power 3 minus x squared minus 5x minus 3 and hence solve this equation equal to 0. So we need to find but a polynomial as this factor if and only if when evaluated at a, the remainder is actually, when evaluated at a, it gives 0, okay? And we know it's a factor when the remainder is 0, right? When x minus 2, when this is divided by that, the remainder is 0. So this is one problem that we are faced with. How do we factorize this? So let's try. So let's see. You say let p of x be the given polynomial. Okay. Okay. Okay, let's try p at minus 1. Let's see what we get when we evaluate the given polynomial at least. It's going to give us minus 1 to the power 3, minus 1 to the power 2, minus 5, minus 1, minus 3. So if we find 0, then we can conclude that x minus 1, which is x plus 1, is a factor. That's what this is saying. It's the factor of the given polynomial. That's what it is saying. if, okay, so when this is evaluated, let's see what we get. We have minus 1 plus 5 minus 3. But this is minus 2 plus 5, that will be 3 minus 3. So it gives us 0. So by this, saying when a polynomial is evaluated at some number a, if the value that you get is 0, then x minus that number which is sitting here must be a factor of this. That's what it is saying. Therefore, by factor theorem, P of x can be written as it's a factor, so it can be written as x plus 1 times some polynomial here. That's what it is saying. It's a factor. It means you can write something like this. That's what it is saying. Very, very important. Okay? That's what it is important. Okay. So, so we have found one factor. So what is this qx? What is this qx? Alternative side, when we write this into the given polynomial, it's giving us the remainder should be 0. That's what it is saying here. For this to be called a factor of that. So this q of x, you can use the synthetic division. Let's use the synthetic division. When is this going to be? When x is minus 1. And then I write this, the coefficients 1, minus 1, minus 5, minus 3. So we can bring down this 1 here. Then this times that is minus 1, add minus 2. That is 2 minus 3. Then this times that, it is 3. So when we put there, when we add, it will be 0. This is the remainder. And this is the quotient. So this constant x, then x squared. So the q of x here, which is the quotient, is x squared minus 2x minus 3. So therefore, what we are saying is, we are saying the given x to the power 3 minus x squared minus 5x minus 3, because x plus 1 is a factor, we can write it as x plus 1, and the quotient is this one. So x minus 2, x minus 3. And of course, we can check if we can factorize, because this is quadratic. Let's check if we can factorize this. You see, if you think of minus 3 and 1, when you multiply this, you get minus 3. And when you add, you get minus 2, the coefficient of x. So those work. So this I can write x plus 1, and I factorize our x minus 3, and then x plus 1, right? Again, x plus 1. But you can also write this as x plus 1 whole squared, then have this. Okay, it is factored nicely. So once you have managed to do that, solving this will be easy, right? Yes, to be straightforward. So therefore, we are saying x to the power 2 minus 5x minus 3, which in factored form, it is x plus 1 squared, then x minus 3. We are saying equated to 0, right? And this would mean that either x plus 1 squared is the one which is 0, or x minus 3 is 0. That's what we are saying. But the square of any number, if you are told the square of any number is 0, then the number in question is the one which is 0. So here it means x plus 1 is the one which is 0, or x is 3. But this one gives x is minus 1, or x is 3. So these are the solutions. So your x, either your x is -1, or our x is 3. That's how we can use the factor theorem. But there's another version of which may prove to be useful. So we restate the factor theorem as follows. Factor theorem. So let P of x be a polynomial. Then A, if x minus A is a factor of the polynomial, then this should happen. B, if a polynomial is evaluated at A, we are getting 0, then x minus A is a factor of P of x. So I'll not provide the proof. We now move on to the rational zeros theorem. Rational zeros theorem. Rational zeros theorem. So if P over Q is a rational number, written in lowest terms, and if P of Q is a 0 or root of the function f, which is a polynomial function, with the integer coefficients, then P is a factor of the constant term and Q, which is the denominator, is a factor of the leading coefficient, So So I can provide a proof here. We are saying if this rational number is a zero of this polynomial, okay, with integer coefficients, then we can say that then the p, which is the numerator, is supposed to be a factor of the constant term in the polynomial function, and the denominator q is supposed to be the factor of the leading coefficient. That is the claim. So we are assuming this p over q, which is written in lowest terms, is actually a zero or a root for a given polynomial whose coefficients are integers. So we can say, so f evaluated at p over q, because we have said it is a zero, so it's a zero or a root. It means when f is evaluated at that point, at that number, the result is zero. So the justification is that because p of q is a zero of f, so it's a zero of f of x. Now let's see what it takes us to. F evaluated at p over q, remember the polynomial we said, I think I said it's an x to the power n plus an minus 1 x to the power n minus 1 plus a2x squared plus a1x plus. So this is the form of a polynomial. So if you put everything here, it will be an t over q to the power n plus an minus 1 t over q to the power n minus 1 plus a1 t over q then plus a0. But we are saying this is equal to 0, right? Okay, so next we are going to multiply throughout by q to the power n. So if I do that, I'll end up having an t to the power n. Remember, I'm multiplying throughout by q to the power n. Okay, so I'll have this, then plus an minus 1 t to the power n minus 1 here, multiplying by q, q to the power n, and this is q, we are dividing. It's like you have p to the power n over q to the power n minus 1. So definitely, this is bigger than this. So you can write p to the power n minus 1, then p, right? Over, what are we doing here? Sorry. I think it should be, I'm trying to, second term, it's an minus 1 t to the power n minus 1 over q to the power n minus 1. I'm multiplying each power by this. So these two, it will be q to the power n minus n plus 1, which will be q to the power, and this is just q, right? So here we'll just bring about q plus, then we come to the next one. Remember we have p, so these they will be multiplying by q to the power n. Q to the power n, so it will be q to the power n minus 1 plus a0 q to the power n equal to 0. And this one, it will be p to the power n plus an minus 1 p n minus 1 q plus a1 t q n minus 1 is equal to, subtracting this from both sides, it will give us this one. Okay, yeah, so okay, so that's what we get. So in here we can try to factor out, I think there's a common factor here, p. So factorize p. If you factor out p, let's see what is left. An p. Remember, if you take out p here, you remain with p to the power n minus 1. And if you take out p from p to the power n minus 1, remain with p n minus 2q plus, if you take out, so here you have this n minus 1. Okay, so you have factorized and you are saying a0 times q to the power n. There's one interesting thing. We said p over q, this is a rational number written in lowest terms. So, okay, there is between p and q, we don't have any common factor other than 1, right? So, but this is saying this quantity is equal to p times this, where this p is not a factor of, they don't have any common factor with q. So definitely, it follows that this a0 is the one, a0 is the one which is the one which is a factor here, surely. So you can write that this result shows that negative q to the power n equals the product of the two factors, p and what is inside the brackets, p and n p to the power n minus 1 plus a1 q to the power n minus 1. Okay. For this reason, p must be a factor which is in this the 0 there, which is the numerator. The numerator p must be a factor of minus a0 q to the power n. So the numerator must definitely be a factor of those guys. Okay, so because it was assumed that p over q is written in lowest terms. So therefore p and q have no common factors other than 1. So P is not a factor. P is not a factor of Q to the power n. Thus, P must be a factor of the leading coefficient, of the constant coefficient in the polynomial, in the given polynomial, the constant coefficient A0. In a similar way, just changing the rows, in a similar way, it can be shown that Q is a factor, which is the denominator of the proposed zero, is a factor of the leading coefficient, A0. So, example. Consider the polynomial function f of x equals 6x to the power 4 plus 7x to the power 3 minus 2x squared minus 3x plus 2. So A, list all possible rational zeros, all those values that of x which will make this quantity zero. Those are the zeros, or we call them roots. These are all possible rational zeros. B, find all rational zeros and factor the given polynomial into linear factors. So let's do it together and see how it works. So, solution. So, any rational zeros of a polynomial of the form P over Q. So, let P over Q be a rational zero or root of f of x. Then P is a factor of the constant coefficient, and Q, which is the denominator, is a factor of the leading coefficient. Let's see what we are saying. So in this particular case, P is factor of 2. Okay, that is, so it's a factor of 2. So P can be either plus or minus 1 or plus or minus 2. So those are the factors of 2. The denominator is a factor of 6. That is Q can be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. These are the factors of 6. Therefore, P over Q, the combinations, we can have this over this, plus or minus 1, can either be plus or minus 1, or we can have, I've said this over that, then this over this, which is plus or minus 1 over 2, plus or minus 1 over 3, plus or minus 1 over 6. Then this over that is plus or minus 2. This and that, plus or minus 1, we have already listed it. Then we have plus or minus 2 over 3. And then the next one is plus or minus 1 over 3, which is already listed. So this can be n of this. Can be n of this. So how do we check? So list all possible rational zeros. These are the possible rational zeros. So in the next part of the question, we are asked to find all the rational zeros and factor into linear factors, all the rational zeros. So there is a simple way to check for the first part, this one. There is a simple way of checking. Simple way of checking. We are given f of x equals 6x to the power 4 plus 7x to the power 3 minus 2x minus 3x plus 2. Okay? Okay. So we can check if 1 is a 0 of that polynomial. All you can do is it's not. We can just maybe when we get to it, but you can just add these guys. If it gives you 0, then that is to be a 0 of that. So 6 plus 7, 13 minus 2 minus 3 plus the constant. So if you add this is 1 minus 3. Okay, this is 1 minus 2 plus 2. It gives us 0. So it means x equal to 1 is actually a 0. It is a 0 of this. You can check, it's not difficult. Let's see, I'm going to use the synthetic 1 here. I want to show that 1 is a 0 of this. Okay, I have 6, 7, minus 12, minus 3, and 2. So bring down your 6. So we have 6, 13. I'll put 13 here. 1 minus 2. Okay, minus 2. So the last number is your remainder. So indeed, f of 1 is 0, and x minus 1. And x minus 1 is a factor of f of x. That's what it is saying. So this problem that we are given here, so f of x can be written as x minus 1 times, this is the quotient, 6x to the power x to the power 2, x to the power 3, x squared plus x, then minus 2. So we can continue to check until we factorize this. If we use the same trick, 1 to see if the 1 or minus 1 are the zeros of this quotient, the resulting quotient. You can add this. Definitely it will not give you that. So what you do is, okay, so 1 is not a zero of that, because, so just write this, you say x equals 1 is not a zero of not f of x of 6x to the power 3 plus 13x squared plus x minus 2. Because when we add the coefficients, the sum is not 1. This is 19, 20 minus 2 to be 18. But so what we do is, we now check if x equals minus 1 is a 0 of 6x, 13x squared plus x minus 2. So to do this, you look at all those terms where the power is an odd number. You change the signs, okay? Change the signs for all those terms where the power is an odd number. So that's what you do. So the first, this is an odd number, so I'll change the sign. I'll write like this. This is even, so unchanged. This is odd power, I'll change the sign. And this is the x to the power 0, which is even, so I'll leave it unchanged. This time, if I add, I'll have minus 6 plus 13 minus 1 minus, let's see what we get. This is 7 minus 1 minus 2. So it's failing to work out. So we see that it is also not a solution. It's not a 0 or a root of the given function. So we have to try others. Think we are plus or minus 1, plus or minus 2. So let's try minus 2. Let your x be minus 2. Let's see if this will be a 0. So we are going to just put minus 2 here, and then we get these coefficients, the ones that are left there. We have 6, 13, 1, minus 2. Let's see what we get. So we have 6, that's minus 12, add 1, minus 2, minus 1, that is 2, 0. We are lucky. So therefore, x equals minus 2 is a 0 of 6x to the power 3, 13x squared plus x minus 2. Okay, so if this is a 0, what it means is that, it's a 0 of that, it also means that means that x plus 2, therefore x plus 2, we can say thus x plus 2 is a factor of 6, 13x squared plus x minus 1. So it's a factor. So if it's a factor, look here. So we can therefore, so this is our f of x. So we can write that x minus 1. This one we are taught it has a factor, this one. So I can decompose this one as x plus 2. And the quotient from here, we can read it is 6x squared plus x minus 1. Okay? That's what we have here. Let's see if we can factorize this. This is quadratic function which we can easily work it out. So x plus 2, that is okay. So we have minus 6. So 6 minus 1. I think it works. So we can write this as 6x squared plus 6x minus x minus 1, right? And this will be x minus 1, x plus 2. So working out this one, it will be 6x, x plus 1 minus 1, x plus 1, right? So we have x minus 1 into x plus 2. From here, we have x plus 1 and 6x minus 1. I think, why did we get this from here? Okay, so this our function is factored as follows. So it will be this x plus 1 and 6x minus 1. So it is factored completely. And this so it is factored as indicated there. So caution, to apply the rational zeros theorem to a polynomial with fractional coefficients multiply through by the least common denominator of all the fractions. So intermediate value theorem for polynomial functions, So let f be a polynomial with real number coefficients. If f evaluated at A and f evaluated at B have opposite signs, then there is at least one value of C between A and B such that f evaluated at C is 0. Equivalently, the equation f of x equal to 0 has at least one real root between A and B. If the value at A, the value at B are opposite signs. So example, show that f of x equals x to the power 3 minus 2x minus 5 has a real 0 between 2 and 3. So it's just a question of checking. F at 2, you can check 2, 3, 2, 2 minus 5. I think this will give you minus 1, it's negative. And F at 3, 3, 2, 3 minus 5, I think it gives us 16. So you can see at 2, it's negative, at 3, and it makes sense because at 2, at 3, look here, at 2, it picks -1 somewhere there. Then at 3, it picks 16. It's somewhere here. So the graph passes through that point. At 2, it passes. So it means it must have crossed somewhere here to come up there. Definitely. Okay, rational functions are quite important, so we'll spend some time to look at them. So let's look at rational functions. Rational functions. Rational functions are quotients. Quotients of polynomial functions. This means that rational functions can be expressed as f of x equals p of x over q of x, where p and q are polynomial functions. And of course, the value that q assigns to x is different from 0, because we cannot allow it. We'll be dividing by 0, which is disallowed in mathematics. The domain of a rational function is the set of Oreos except the x values that make the denominator 0. Make the denominator 0. Example, let a rational function, we have a polynomial sitting there over, this is expanded into linear, this is factored into linear factors, it's also a polynomial. So, domain of f denoted by d of f is just the set of Ox such that this cannot be 0, this x cannot be -5, it cannot be 0, it cannot be 2. But it can take the rest of the values. This A. B, if you have h of x equals x plus 5 over x squared plus 25, you see that this one can admit any real number. Any real number. There is no real number that can make this denominator equal to. So when you look at the denominator here, is actually x squared plus 25. So, but x squared, you know it is greater or equal to 0 all the time. So therefore, we expect x squared plus 25 to be always greater than or equal to 0 plus 25. Yeah, or similarly, you can add 25 to both sides of this inequality. You're allowed, and you get this. So this quantity is always greater than or equal to 25. So it's actually it is, you know, the graph which passes through this one. It is y equals x squared. So when I add 25, it means I'm just increasing. It passes through 0, so it will be lifted up there, and it will go like this. So this is y equals x squared plus 25. It is the one which is shifted vertically 25 units from the origin. Okay, so this point is shifted, and every point on here it is shifted the same number of units vertically. So that's the graph. We'll now look at what we call the reciprocal function. The reciprocal function. Very, very interesting function. The reciprocal function. Reciprocal function. This is f of x equals 1 over x. This is the reciprocal function. So this is a very, we can sketch the graph of f of x equals 1 over x. You see that note that f as the graph of f has no x-intercepts. It has no x-intercepts and y-intercepts. Okay, so it looks like this. This is the x, this is y. It's not defined there. So you see that if you increase this, the values, positive values of x, this number will be getting smaller and smaller. Okay? And if you approach 0, you put numbers like, when I say, I write, I'm approaching, if I say I'm approaching, this is x approaching 0 from the left, it means I'm coming like this. If I say, I write like this, it means I'm approaching 0 from the right, okay? So you see that when I approach 0 from the right, which is this one, I'm coming here. Approaching 0 from the left, it means I'm going towards it like this. I'm taking those values. You will see that the numbers, this will be getting smaller and smaller, but they will never be equal to 0. And as I'm getting towards 0 from the right, these numbers are getting bigger and bigger, but they will never touch this. Okay, they are getting bigger and bigger. Similarly, you can see that when we approach 0 from this, we'll be getting numbers, will be getting smaller and smaller, getting larger in the negative sense. And then when we go this way, it's getting smaller and smaller, but always remaining always remaining negative, but approaching 0 like that. So this is the graph of f of x equals 1 over x. This is how it looks like. So it exists in the first quadrant and in the third quadrant. Okay. So anyway, this will help us to talk about the vertical and horizontal asymptotes. Vertical and horizontal asymptotes. Vertical asymptotes of rational functions. Definition: the line x equal to a is a vertical asymptote. We'll abbreviate it like that, of the graph of a function f if f of x increases. So it means the values that the function f assigns to x, those values are increases or decreases without bound as x approaches a. Approaching a can approach it either from the left or from the right. So we have, this is your x, this is your y. So if we are told this is a vertical asymptote, and this is x equals a, so this point there, it is a comma 0, then so you can see that when we approach a from the right, so it means the graph is coming like this. Okay, so we can say as x is approached from the right, we see that the that the function assigns to x are increasing and bounded. So this is how we write. So as we are taking values, as we are approaching a from the right and evaluating this function, the function values are, you see they are becoming bigger and bigger. This is so it means it will look like that. Okay. So we can also approach a from the left, and how does it look? So if we approach, this is your x, this is your y, and this is the vertical asymptote, vertical asymptote. So what we are saying is, this is your a comma 0, which is this point. So we are saying when we approach it from the left, so we expect this is what is happening. So we approach that vertical line asymptotically, we will not touch it. So this say as a is approached from the left, the values are growing, are increasing and bounded. We also have other situations where the values of this can decrease and bounded. So this we can have, this is x equal to a. It's also possible that this is a. So as we approach a, we are having something like this. So as a is approached from the left, the functional values are decreasing and bounded, meaning they are going to negative infinity. Okay. The other situation could be this one. This is your y, this is your x. This is your y, this is our x. So the other one would be, you can approach this from the right, and when we approach, the graph is looking like this. So meaning as a is approached from the right, the values are growing, are decreasing and bounded, because it's going to negative infinity. So how do we locate vertical asymptotes? Look at locating vertical asymptotes. So if f of x, which is p of x over q of x, is a rational function in which p of x and q of x have no common factors, and a is a 0 of q of x, the denominator, then the vertical line x equal to A is a vertical asymptote. The vertical asymptote of the graph of F. Example, can quickly look at some examples. Find the vertical asymptotes, if any, of the graph of the following. Rational functions. F of x equals x over x squared. B, g of x equals x plus 3 over x squared minus 9. C, h of x equals x plus 3 over x squared plus 9. So solution A. So the vertical asymptotes are those x values, assuming that the rational function given has no common factors, as we've seen there. F of x, x over x squared minus 9. You can also rewrite it as x minus 3 and x plus 3. Okay? So the vertical asymptotes are those x values that will make this denominator 0. So therefore, vertical asymptotes here are x equals minus 3 and x equals 3. B, g of x equals x plus 3 over x squared minus 9. You can write this as x minus 3 and x plus 3. So there is a common factor here. So you see that this is going to be 1 over x minus 3, provided x is not equal to minus 3, right? So, therefore, the only vertical asymptote is x equal to 3. Of course, in C, there is no vertical asymptote there. No vertical asymptote exists because this can never be equal to 0. There's no x value which will ever make x squared plus 9 0. So we can say a value where the denominator of a rational function is 0 does not necessarily result in a vertical asymptote. The value A causes the denominator to be 0, but there is a reduced form of the functions equation in which A does not cause the denominator to be 0. Example, find the vertical asymptote of f of x equals x squared minus this x minus 2. So, solution, not here, x equal to 2 makes the denominator 0, but it is not a vertical asymptote because the numerator is also 0 at this point. Therefore, there should be a common factor. Okay, so that factor must be cancelled from both the numerator and denominator before we can determine the vertical asymptote. So now x equal to this equals to x squared minus 4 over x minus 2. You see this would be that x plus 2 over x minus 2. Okay, this can be equal to x plus 2 if x is not 2, because we can cancel that, right? You can see that this is a linear equation, there's no vertical asymptote at all. So let's look at the definition of a horizontal asymptote. So from now onwards, we'll denote it by H. A. The line y equals b is a horizontal asymptote of the graph of a function f if the function of values approach b as x increases or decreases without bound. So recall that a rational function may have several vertical asymptotes. In contrast, it can have at most one horizontal asymptote. Although a graph can never cross or intersect a vertical asymptote, it may cross its horizontal asymptote. That's important to note. So how do we locate horizontal asymptotes? So let f be a rational function. It is a rational function given by f of x equals an x to the power n plus an minus 1 x to the power n minus 1 plus a1 x plus a0. This is one polynomial. Another polynomial of degree m, bn minus 1 xm minus 1 plus b1 x plus b0. Of course, it's assumed as an is not 0 and bn, the leading coefficients are not 0. The degree of the numerator is n. The degree of the denominator is m. As you can see, this is that's the highest. Those are in the numerator, the highest power is n, and in the denominator it's m. So 1, if the degree in the numerator is smaller than the degree in the denominator, then the x-axis, or y equals 0, is the horizontal asymptote. 2, if n is m, the line y equals nx, that is what we are saying, bmxm. Remember, under this assumption, this will cancel, and you are going to have an over bm is the horizontal asymptote, Three, if n, the degree in the numerator, is bigger than the degree in the denominator, then the graph of f has no horizontal asymptote. Example, find the horizontal asymptote if there is one of the graph of each rational function. F of x equals 4x over 2x squared plus 1. G of x equals 4x squared over 2x squared plus 1. And C, h of x equals 4x to the power 3 over 2x squared plus 1. So just implement what we have here. So in A, f of x, we need to look at the degree here is 1, and the degree in the denominator is 2. So this one is saying, if the degree in the numerator is smaller than the degree in the denominator, then the x-axis of y equal to 0 is the vertical asymptote. However, if the two powers are the same, then the horizontal asymptote will just be the ratio of the leading coefficients. Okay, so in this particular case, you can see the degree of that is smaller than the degree of this part. Therefore, okay, so in this particular case, I think the horizontal asymptote is y equal to 0. In B, the degree is the same. So y equals 4 over 2, which is 2, is the horizontal asymptote. Here, it's the other way. The degree there is bigger than the degree there, so there is no horizontal asymptote. So in C, no horizontal asymptote, because this is the third condition. So next we'll look at the graph of rational functions. So today's session ends here. We'll continue next time on how to sketch the graphs of rational functions. Thank you so much.